Hi there, this is Dr. Hisham Said. So we'll continue with this lesson on axial deformations. The last part of this lesson, we introduced the idea that deformation information can help us to solve statically indeterminate members and structures with focus on axially loaded members. So we kind of introduced that there are two methods, the redundant force method and kinematics. We're dealing with the first method here, and which is dependent on superposition concept. And in this part here, we'll see how redundant force method works. This is a kind of in writing how it works. So you would remove a redundant support and replace it with its unknown support reactions in a separate version of that member. And the idea now is we have two or multiple versions of the member. You superimpose the reflections from each case or each version of that member in a way to maintain the original support constraints. So I know it's not clear yet, so we'll clarify it with an example. So revisiting that example we've seen in the first parts of this lesson. So we have fixed supports at A and C and a load at point B. And we know that there are two reactions, FA and FC. We tried to do the statics and equilibrium of this member to solve for the two unknowns. We couldn't, we only have one equation. So the redundant force method is kind of from its name, it calls for removing a redundant support. So the problem we are in is we have too many supports in this case. So one of these supports at A or C is redundant, is not actually needed. So the idea is to remove one of these supports to become the redundant support. So that will be the case here. I will remove, let's say, support C. And in this case, once you remove the support, the member will be free to deform, which was not the case before. So we'll have this member now elongate because I can see this point B pull it down. So it's kind of being tensioned here. And that elongation will be delta C1. Remember that that's not the original beam. I'm just making a version of it that actually I can solve. So I took out the redundant support at C. So, but I have here this kind of equality here, that left case of the system is equal to the right, so it's not correct yet. So what happens is I will consider another system which of that relaxed rod here or column, but now instead of having now the original load P, I will remove that, and now I will focus on getting back to the original version of that member, which is by putting back a force at point C that's equal to the unknown reaction and the redundant reaction that I took from the original case of that member. So now I'm putting FC back with no other loading, no other external loading here. So when I put FC back, I'm now trying to compress C under FC with delta C2. So now I remove the reaction, I remove the support, so the member AC is free to elongate. Now I represent the support by putting back its reaction, FC, and that should be countering that deformation that happens in the first case, delta C1, by a deformation delta C2. So now I guess you know where I'm going with that, is support C is fixed. So delta C in the original case should be equal to 0. Now delta C from the superposition concept is equal to delta C1 plus delta C2. So now I can make a conclusion that delta C1 plus delta C2 is equal to 0, or they actually are equal and opposite in direction. So knowing the information that delta is equal to PL over AE, I just need to calculate each one, plug it in that condition now. This is kind of my second equation beside the equilibrium equation to be able to solve for the two unknowns I have, FA and FC. So Trying to get some statics here, simple one for the two cases here. The reaction in the first case here is equal to P going up, and the reaction at A here is equal to Fc going down. So this means that length AB in the first case is under tension. Length BC is not under any internal forces and stresses. So this means that delta C1 results from the elongation of part AB due to the internal force of tension P. Now, if I do the same here for the second case, the whole length here AC, length L, AC, is under compression force Fc. So that delta C2, that contraction here happens because of that whole length is under compression internal force of Fc. And you can see here that I'm plugging in Fc here negative to represent that compressive action. And that also kind of makes sense because if the delta C1 is positive, delta C2 should be negative, so they can cancel each other. So by solving for this formula here, I'll be able to see that Fc is equal to 3p over 5. So kind of I already got one of the two unknowns that I was missing. So going back to the equilibrium, kind of redoing it from the part before this part, I know in the original beam case or the original column case here, Fa plus Fc negative p is equal to 0, and that was my second equation. If I plug in Fc value that I had before, I will find that Fa is equal to 2p over 5. So that's it. I solved my problem by knowing the deformation information here. I kind of relaxed the problem by removing the redundant reaction and allowed the beam to deform under the loads that I have. And then using the concept of superposition to stick to the original case of that column and its loading, I consider that relaxed column again, but now with no external load, I put back, represented that redundant reaction that I took in the beginning in case 1. Now I have a second case. Adding case 1 and 2 impacts together, that will represent the original case I had. And I was able here to solve for the two unknowns. So that was the first method to solve statically indeterminate members. And the next part of this lesson, the last part, we'll see the second method, which is using kinematics and also the information about deformations to solve for the same problem, but in slightly different way. Thank you. Have a good day.